We are Group 59 and we worked on fraud detection using neural networks. Financial frauds cost billions annually, and rule-based systems often miss new fraud patterns. This project uses PaySim dataset to train a neural network that classifies transactions as fraud or not. The goal is to improve accuracy while reducing the false positive to enhance security in digital payments. Now, what motivated us to do it? Frauds are rising. In 2024, losses hit 12.5 billion, a 25% increase. With online payments growing, manual checks aren't enough. Rule-based systems can adapt, but neural networks can learn complex evolving fraud behaviors. Better detection means safer system and more user trust. The dataset is PaySim, a simulated mobile money dataset modeled after real financial transactions. It has millions of entries with transaction type, amounts, account type, and a fraud label. As you can see in the plot on the left, the fraud label is extremely imbalanced. Only about 8,200 fraud cases out of 6.3 million transactions. That's less than 0.15%. On the right, you can see the breakdown of fraud distribution by transaction type. Certain types like transfer and cash out are more likely to be fraudulent, while types like payment and cash in are almost always legitimate. Here are a few graphs. That's the EDA for our dataset.
So we chose random forest as our baseline model, and we chose the number of estimators as 100. So that means that we'll have 100 individual decision trees that are bootstrapped to vote on whether a particular transaction is fraudulent or not. It is relevant for our dataset and our problem statement because it uses techniques like bagging and feature importance scores to uh, detect fraudulent indicators based on the given features, and which makes it a simple but effective baseline. So as you can see, it performs quite well on the majority class, getting a perfect score. But for the minority class, its recall is low, only at 72%. So our goal with moving forward is to improve that recall for the minority class. This is the ROC and the precision recall curve for the baseline model. So moving forward, we'll be using data pre-processing technique called Smooth for all the other models. Smooth is a technique that allows you to create more samples of the minority class by interpolating the existing instances. This can help a model train better even in the case of an imbalanced data set, which is relevant for our case.
This is our first model, MLP. It stands for multi-layer perceptron. This is a fully connected neural network that learns from numeric features using nonlinear layers. After pre-processing, which included one-hot encoding, feature hashing, smoke, and scaling, each transaction becomes a vector of 14 to 18 features. The model has 3 dense layers with ReLU, batch norm, and dropout. The output is a sigmoid, giving the probability of fraud. Compared to random forest, MLP takes more time to train, but it's better in learning complex patterns. Now, these are the metrics. A threshold of 0.82, MLP achieves 92% recall and 53% precision on fraud, compared to random forest, which had 95% precision, but only 72% recall. MLP trades a few false alarms for catching more frauds. The macro F1 score is 0.84. The overall accuracy is high, though skewed due to class imbalance. Now here comes the ROC curve, PR curve, and threshold tuning. Here are the evaluation plots for the MLP. The ROC AUC is 1, meaning near perfect separation between fraud and non-fraud. The PR curve shows strong performance on fraud with PR AUC of 0.89. On the right, the threshold tuning plot, I tested cutoff from 0.1 to 0.99 and picked 0.82, which gave the best F1 score.
So for a second model, we use CNN, which is built upon the previous classical MLP model. So this uses shared filters to slide out the input to learn about local patterns, which is useful for a transaction dataset. The architecture is given here, but basically the input is the encoded features and the output will be a probability, which implies that you can actually use the threshold as a hyperparameter. And CNN also has fast and efficient inference for predicting whether a transaction is fraudulent or not. And these are the results of the CNN model. For the majority class, it performs quite well, getting 99.9% scores for everything. For the minority class, it has much better recall for the chosen threshold of 0.9 with a slightly lower precision than the baseline model. So as you can see here, there is an inverse relation between the precision and recall. So the more higher threshold you go, the recall reduces and precision increases.
Moving on to the third model, we chose XGBoost. It is an ensemble technique that builds decision tree sequentially, with each tree learning to correct errors made by the previous one. For this model, we used 14 vectors of each transaction. The pre-processing pipeline involved feature selection, feature hashing, one-hot encoding, standard scaling, and smooth for balancing the classes, and fine-tuning the hyperparameters involving like max dev to control the tree complexity, learning rate, in estimators and scale positive weight to adjust the weight of fraudulent transactions in the loss function. In terms of performance, we achieved perfect precision recall in non-fraudulent transactions. And coming on to the fraudulent one, we achieved a 0.83 precision and 0.91 recall, and which gave us a balanced F1 score of 0.87. And moving on to the graphs, so we visualized a rock curve and precision recall curve. So this gives us understanding of trade-off between the precision and recall at various decision threshold levels. And finally, comparing the results, we see XGBoost appears to perform the best overall. Regarding the prior experience, we haven't worked on this exact project before, but we do have experiences in other AI and machine learning applications. And here are the references that we used in this presentation. Thank you.